Hello, my name is Xingyi Wu. Today for the March meeting presentation, I'm going to talk about uniaxial strain effect on superconductivity in 1D lanthanum aluminate strontium titanate channels. Before I start with the topic, I'd like to thank our collaborators, both at University of Pittsburgh and University of Wisconsin-Madison, and generous funders. Now let's begin. We work in the field of correlated nanoelectronics, which arises from two well-established fields. On the one side, we have the correlated electron physics, which is often studied in bulk materials and has shown superconductivity properties. On the other side, we have semiconductor electronics, which allows us to have single electron control and thereby study the quantum system. At the interface of the two is interface heterostructures, which allows us to have both. We are interested in lanthanum aluminate strontium titanate heterostructure. It has been shown in 2004 that there is a high mobility to the electron liquid at the interface. When the lanthanum aluminate layers are 4-unit cell, we can tune the interface to insulator and metal transition. The system has also found superconductivity, magnetism, and tunable spin-orbit coupling. In this talk, we're interested in superconductivity. It has been found in 2007 that this heterostructure undergoes a superconducting phase transition at around 200 millikelvin. Critical temperature can be controlled by electric field, and the phase transition diagram is shaped like a superconducting dome. In the system, people have also found temperature and gate-dependent superconducting gap. These are interesting features that are similar to what's been seen in high-temperature superconductors. There are many hypotheses in the superconducting mechanism. One of them is ferroelastic domain. It has been demonstrated by Pai et al. That electron-pairing and superconductivity exist at conductive channel edges, which is also ferroelastic domain walls. To further explore why this heterostructure is a superconductor, we combine this material with strain engineer techniques. There has been many studies on the strain effect on superconducting phase transition temperature Tc of bulk strontium titanate. Early experiments observed decreases in critical temperature under hydrostatic pressure, while seeing both increase and decrease for compression along 100 axis. Theoretical calculations predicted a linear dependence on uniaxial and biaxial strain, meaning that the transition temperature decreases when the sample is compressed, increases when it is stretched. This is supported by a recent experiment where they saw a nearly 50% increase in critical temperature in niobium-doped strontium titanate under tensile strain of 0.05%. We think it is appealing to see what would happen if we strain the lanthanum aluminate strontium titanate heterostructures. Our experiment uses a conductive atomic force microscope lithography, c-AFM lithography, to pattern interface on nanoscale. We start with lanthanum aluminate strontium titanate, about 3.4 unit cell, so it is insulating to begin with. We make electrical contacts to the interface. If we take a conductive AFM tip, apply a positive voltage to the tip, and move it across the surface of the material, it will deposit protons and attract electrons, creating conductive channels. The process is reversible. If we apply a negative voltage, we could erase the structures and create barriers. These nanostructures can be as small as 2 nanometers Nanowires created in this method undergoes superconducting phase transition at 300 millikelvin. For strain engineering, our experiment uses a strain cell by Rizobel company. From the picture on top, you can see our 5 mm by 5 mm sample attached on 2 piezo stacks in the strain cell. We create 4-terminal nanowire device at room temperature and do strain-dependent transport measurement at 50 millikelvin, which is below superconducting phase transition temperature for the system without any strain. When we apply a positive V strain voltage to the strain cell, the sample will be under uniaxial tensile strain. When we apply a negative V strain voltage, the sample will be uniaxially compressed. We calculate the actual strain from displacement of the sample, which is measured by capacitance change. This page shows result of our 4-terminal resistance of a 3 micrometer long nanowire. It is aligned with uniaxial strain direction. We plot resistance as a function of current and strain. This data is taken when we continuously change the uniaxial strain from tensile to compressed. To see the features better, we plotted Y line cuts of the intensity graph at some strain values. You can see the purple colored regions, which is superconducting state, and the corresponding superconducting gap. But there are also some strain-induced not superconducting state. We observe the smooth change in superconducting critical current. Furthermore, we sweep the strain back and forth between tensile and compressed and observed hysteresis. This page shows result when we sweep the strain continuously from compressed to strain, and again we observed strain-induced not superconducting states. Now we discuss the preliminary data in the context of ferroelastic domain hypothesis. Strontium titanate undergoes a cubic to tetragonal ferroelastic antiferrodistortive transition at 105 Kelvin, when X, Y, and Z domains can form. It has been demonstrated that the c-AFM return nanowires, the system that we're measuring, are elongated in Z direction at room temperature, seeding ferroelastic Z domains after that transition under 105 Kelvin. Outside of the conductive channels will be X or Y domains. It has been shown that superconductivity exists in the ferroelastic domain walls that decorates these conductive channel edges. Suppose uniaxial strain moves ferroelastic domain walls. If the walls move towards each other, the center, the conductive Z domains could collapse. If the domain walls move away from the center, their overlap with the high electron density regions decreases. In both cases, superconductivity could be destroyed. To sum up, we used a c-AFM lithography method to create nanowires at lanthanum aluminate strontium titanate interfaces at room temperature. These systems will become one-dimensional superconducting system at 50 millikelvin when we used a strain cell to apply external uniaxial tensile and compressive strain. We observed emergence of non-superconducting state due to those strains. Based on that, we proposed the hypothesis that the strain could move the ferroelastic domain boundaries in those one-dimensional conductive system, and it would destroy superconductivity. That is all. Thank you for your attention. And finally, this is a group picture of LevyLab from University of Pittsburgh, and there are many other talks that my colleagues will be presenting and uploading videos in the APS March meeting website. Thank you.